All right, so here's what's going to happen. We have our descriptive statistics review. I'm going to walk through this problem by problem, and I will timestamp each question, and that way, if you want to skip to certain questions, you can. I'll publish a key for that. So anyway, question number one is going to roll in here at 18 seconds. All right, so it says that I gotta find the right pin. Let's try again. I suppose a normal model describes the acidity of pH of rainwater, and that water tested after last week's storm had a z-score of 1.8. This means the acidity of the rain has. Now, so we have to remember what exactly is a z-score. The z-score is it is the number of standard deviations above or below the mean. Okay, I'm zoomed in a little tight. Okay, try that instead. So with that in mind, here we go. Let's go through the answers. So we had a pH of 1.8, variable standard deviation. We want to be 1.8 standard deviations higher than the average rainwater. So E is going to be the answer that we're shooting for here. I know on the bell work, I know sometimes we forget that above or below, but we got to remember that if we're asked to describe a z-score, that's what we have to include. All right, so at 143 is problem number two. Which of the following can stem plots show? So we have to remember what a stem plot is. A stem plot's going to have a stem. So here's 0. We'll follow that with a 2 and a 2 and a 3 and a 4. So this is 2, 2, 3, and 4. This would be 11 and a 17 and a 17 and an 18 and a 19, etc. So the 2s and 3s and 4s. So there's a 41. Okay. So can we show symmetry? Yeah, we could. If I had drawn a symmetric stem plot, it would show symmetry. Does it show gaps? Absolutely. It shows the gap right here. Clusters, it would do that. And lastly, outliers, again, it's going to show location and position. So therefore, it's outliers as well. So this one's going to be E, all of the above. Okay. All right. Number three is checking in at 236. Suppose we define a new measurement as a difference between the 60th and 40th percentile scores in a population. This measurement will be giving information concerning what? So if we're talking about percentiles, we know we have ones from the 25th to the 75th percentile. We have something of that nature already that is called our inner quartile range. And the inner quartile range is a measurement of variability. So therefore, since we're talking about percentiles, this will also be a measurement of variability. So B is going to be our answer on that one. Okay. All right, this one, question four, is going to roll in at 320. Okay, this is a cumulative relative frequency chart, excuse me, also known as the ogive graph. We'll see another one later when it's called ogive, but this is referring to, again, our cumulative percentile. So it's going to not do individual percentages, but we're going to add and keep a continual running total of the percent. We have to understand that the median is going to be right smack dab in the middle. And so in percentiles, that's going to be the 50th percentile. So we're going to come over here to 50. We're going to dot over and we're going to dot down, and that's around 22. So that is one of my options. So we're going to roll with 22. About what percent of the data lies below 30 miles to the gallon? So on the x-axis is my miles per gallon. We're going to go over to 30. We're going to run that up to there. And then we're going to run it over about 90 percentile, I would guess. That is one of my options, so we're going to go with 90%. Okay. Question five is checking in at 424. Based upon the comparative box plots shown, we can conclude what? So again, this is understanding box plots. We have two box plots, one for set A, one for set B, and we just have to go through and remember characteristics of the box plot. So A and B have the same range. Well, remember, range is your max minus your min. So for A, we are starting at 12 as my max, and it looks like 5 is my min, so that has a range of 7. In B, it starts out, it looks like at 15 up there and down here at 6. And the difference between 15 and 6 is going to give me a 9. So they have the same range is not true. Okay, so 1 is out. So that means we can rule out A and B. Sets A and B have the same interquartile range. So earlier we discussed what the interquartile range was up here. It's your difference between your 75th and 25th percentile. So it's at the distance of your boxes. Okay, so this is quartile 3 minus quartile 1 is your interquartile range. So in this case, for A, it looks like we're going from 10 down to 6. So A is going to have an interquartile range of 4. B is going to go from, it looks like 13 down to 9. It also has an interquartile range of 4. So that's good. And in reality, we didn't even need to check that one because number 2 appears in all the other answers. We could have just ignored that, but it was a good review. All right, 50% of the data in set B lies above 10. Okay, so we have to remember that 10 is going to run, this is my median. That's what that middle line in the box plot is. So that means that I have 50% up above that and 50% will be below that. So that means that's a true statement. 50% will be above 10. Okay, so that is true. So right now we got 2 is true, 3 is true. And lastly, 50% in debt in set A lies below 7. And again, 7 fell on that median. So that means we have 50% above it and we have 50% below it. And we're going to roll with that as a true statement as well. So that means that E here is going to be the best answer because those are the B statements 2, 3, and 4 are correct. Okay. All right. Question 6 is checking in at 6:51. Which of the following sets has the smallest standard deviation? So we have to remember that your standard deviation is, in quick terms, it's the average distance from the mean. Okay, how far each piece is from the middle. So in all of these, if we were to find the mean of this set of data, it comes in at 4. If I did the mean of this set of data, it also comes in at 4, and the mean of this set of data also comes in at 4. So they all three have a mean of 4. Now we're doing the average distance. So that means this is 1 below, this is 2 below, and this is 3 below. So that means that this is 0, this is 1, 2, and 3. So actually everything cancels out on each of these, but we can see that I have some variation as far as how far it is from 0, or from the middle, excuse me. In this one, I've got 3 pieces that are 3 below each. So my deviation is large. I got three that are 3 to the left and 3 that are 3 to the right. And I come over to this set and I've got, yes, this is 3 to the left, but then 4 is going to be a 0, a 0, a 0, a 0, and a 0, and a positive 3. So if we're talking about variation to go into that standard deviation, this has very little variation. So therefore, this has the smallest standard deviation. So 3 is going to check in with the smallest. And this one has the largest deviation because all of its pieces are further from the middle. So the farther they are from the middle, the larger that standard deviation is going to be. So E is going to be my answer. Okay. All right, 835. The mean law school aptitude test for applicants to a particular law school is 650 with a standard deviation of 45. The distribution of scores is approximately normally distributed. So we needed that little piece of information there, normally distributed. Suppose that only applicants with scores higher than 700 are considered. What percent of applicants are considered have scores below 740? Now you are not going to have, again, everything's going to be free response. So we're going to have to possibly draw a curve. Now remember, when we draw a curve, we always want to put a middle to that curve. So we're going to go with 650. Okay. Now we know to be considered, we have to have a score of 700. But we're talking about what percent of applicants have scores below 740. So we're looking for this shaded region right there. Now, because this is my calculator, a normal CDF is what we're going to do on this one. Now, we could find z-scores and percentages and subtract, but for the sake of time, and you have your calculator, even it told us that we're only going to have calculations that could be done with a straightforward, simple function calculator. So They're not going to give us anything crazy. Anyway, 700 is going to be my lower boundary. 740 is going to be my upper boundary. That mean that we're going to put in there is going to be 650. And then we're going to have a standard deviation of 45. So remember, if we're doing this, we have to include our calculator speak. It's going to be a free response question. Anyway, if we went to our calculator and did that, this is going to roll in at 11%. Okay. You measure, oh, 8. 8 is checking in at 10:30. You measure the age and marital status and earned income of a simple random sample of 1,463 women. The number and type of variables you measure is. All right, so we need the number and type of variables. So we have two types of variables. We have categorical, which is going to be some label, and quantitative is going to be some measurement. Okay, it's going to have a unit. These are going to be counts. So age, that's something we can measure in years, so it's going to have a unit. So this is going to be quantitative. Marital status, married, single, other ones, who knows? So that means it's going to be categorical. And lastly, earned income is the other variable. And it's going to be, again, we're going to measure the amount in dollars. So that's going to be quantitative. So that means 2 are quantitative and 1 is categorical. So 2 quantitative, 1 categorical. E is going to be our answer. Okay. All right, number 9, checking in at 11:32. The distribution of the actual weights of 8-ounce chocolate bars produced by a certain machine is normal. So again, we're going to look for that word. With a mean of 8.01 and a standard deviation of 0.1, what weight should they be put on the chocolate bars so that only 1% are underweight? Okay, so once again, this is going to give, we're going to look at this in a curve. We're going to mark the center of this curve. We know that machine is putting out at 8.1 ounces bars, but the actual weight is 8 ounces, but I want this 8-ounce mark. I only want 1% of my candy bars to fall below 8. Okay, so what X value are we after here? Okay, what weight should we put on the chocolate bars? So this is going to be working backwards. We're trying to find a value of X. Okay. Um, right, and actually I should scribble this out. We don't know what's 8. We just know that they're supposed to be 8-ounce bars, but we're going to put a specific value on the chocolate bar. So we don't know what this is. We're trying to find that value. So this is an inverse norm problem. Okay, and we're going to inverse norm, and again, this is you and your calculator again. We can run, because we're finding a value of X, we can run my calculator the entire time. So we have O1, that's my area, followed by an 8.1, which is my mean, followed by a 0.1, which is my standard deviation, and my calculator is going to spit something out for me. Okay, so remember that's found exactly where I found the normal CDF at. We're going to go we're going to second and distribution. We're going to go inverse norm. We're going to have an area of 0.01. We're going to have a mean of 8.1. And we're going to have a standard deviation of 0.1. Let's say left tail. And we're going to paste that. Okay. So we get 7.87, which is answer C. Now, if we're doing this a different way, what would happen is we would have to do an inverse norm. Or we would, inverse norm of 0.01 to get a z-score. That'd give me a negative 2.33. And then we'd have to use the z-score formula. Negative 2.33 is equal to the observed minus the expected divided by my standard deviation. And then algebra is for the win. But that's how we're going to do that by hand, if we needed to do that by hand. As well, we could also, instead of using an inverse norm, we can go to our go to my table. We need to find an area for 1%. So we're going to count here. Here is 0.99 and here is 0.102. So 1% is closest to this. That's a negative 2.3 and 3, negative 2.33, which is exactly what I've got if I'd have ran that in an inverse norm in my calculator. All right, 10 is checking in at 1455. A researcher reports on average, the participants in his study lost 10.4 pounds per 2 months after 2 months on his new diet. A friend of yours comments that she tried the diet for 2 months and she lost no weight. So clearly the report is a fraud. Which of the following statements is correct? Um, so again, we have to remember what it gave us. It gave us that it was on average 10.4 pounds on average. So we're going to have some below that, some above that. It could be as far low as 0. It could be as far above as 20 pounds. Okay, on average it's 10. So we just have to find one that goes best with that. Your friend must not have followed the diet correctly since she did not lose weight. And again, because it's an average, we could have people that lost no weight. Since your friend did not lose weight, the report must not be correct. Again, it goes back to the other reasoning. It's an average. The report only gives an average. It does not imply that all participants lost 10.4 pounds or even lost weight at all. Your friend's experience does not necessarily contradict the results. So that's what we're going to come in at. My friend could have been an outlier. True. However, we don't know. We can't do that specific. In order for the study to be correct, we must now add your friend's results into it. And again, no, it doesn't matter about getting those results into that study. Okay, 11 is checking in. It looks like 16. That's hard to read, but 16.18. That's 1629. A normal body temperature varies by time of day. A series of readings was taken in the temperature of a subject of a body. The mean reading was found to be 36.5 degrees Celsius with a standard deviation of 0.3 degrees Celsius. When converted to Fahrenheit, the mean and standard deviations are done with this conversion. So what it's wanting us to do is it wants us to convert the mean. And I wrote a sample mean, not that I don't know if this is a sample mean or not, but yeah, series of recordings. Okay, so it's going to be a sample mean. Anyway, we have to know what to do. So to get a Fahrenheit reading, we're going to take our Celsius times 1.8 and add 32. So this question is here to remind us what we do when we multiply and add to a set of summary statistics of a set of data. Now, every summary statistic is going to be affected by multiplication. So for the find the mean, we're going to take it times 1.8. And I know we can't see my hands very good, but remember if we have all these pieces here, and I slide them up 32 units on the number line, they are still the same exact distance apart. However, it is 32 units up the number line, and I got ahead of myself because this is talking about standard deviation, and we're still talking about that mean, but every one of those pieces had 32 added to it. That means it's going to increase it by 32. And so that ends up being 97.7. And in reality, you can't see that. But in reality, we didn't have to do that at all because 97.7 is the first answer for each of those. So that was completely irrelevant. We did not have to do that. Okay. Standard deviation, since we're using sample variables here. Again, everything is affected by multiplication. We're going to take it times 1.8. But what we have to remember here is standard deviation. Remember, back to my hands again. Since everything moves up on the number line, it stays the same distance apart, so it's not going to be affected by 32. I am not going to add that, and we're going to get a 0.54. Okay, so that means that C is going to be my answer. Okay, number 12. There are 3 children in a room, ages 3, 4, and 5. A 4-year-old child enters the room. So we have a 3, we have a 4, and we have a 5-year-old in the room. So that obviously has a sample mean of 4. And then another 4-year-old enters the room. Now, what is going to happen? Okay, so we obviously had a mean of 4. We came in, we had another piece of data that was on the mean, so therefore that mean is not going to increase. I mean, we could figure this out if we wanted to. If I take that's 7, that's 12. 12 divided by 3 pieces is going to give me 4. We're adding the other 4-year-olds. So now we have 16 divided by 4. Well, we could figure that out. I mean, we could figure that out numerically, and we did. The mean is going to stay the same. So we can cross off. Mean will decrease or increase. Okay, those are gone. So what do we have here? The variance will increase, the variance will decrease, or they both will stay the same. Okay, so what is going to happen to my standard deviation? So remember, this one was I had one that was one below, I had one that was on zero, and I had another one that was one above. And then I added another one that came in on the middle. So remember, your standard deviation is your average distance from the middle. So my sum stayed the same, but I got another piece of data in there. So that means my variability has to decrease. So here it was increase, here it will stay the same. So we have to decrease. Uh-oh, I missed the timestamp on that. Doggone it. I think I talked about that for a minute. What was my other one? 1629 and it's 20 now. We'll go with something around 18. I'm sorry, I goofed that up. All right, this one's at 20 2040 it looks like. Here's our ogive graph that I mentioned earlier. It actually calls it an ogive. On the number of ounces of alcohol, 1 ounce is about 30 milliliters consumed per week in a sample of 150 students. A study wished to classify the students as light, moderate, heavy, and problem drinkers by the amount of consumed per week. About what percent of students are moderate drinkers? Moderate between 4 and 8 ounces. Okay, so here's 4, and here is 8. Okay, so we want to figure out what portion lies below 4. So we go up here, it pretty much glides over to 20. So I know my low end represents the 20th percentile. My high end of 8 rolls up here to 60, it looks like. So that means in this neighborhood, this area right here is roughly, hard to read, sorry, 40%. Okay, so that's where we're going to roll with that one. 14, it times in at 2143. Which of the following is likely to have a mean that is smaller than the median? Okay, so remember, when we have a distribution of data, if my data is lovely and perfectly normal, then that means my mean and my median will be directly on each other. But it doesn't necessarily have to be normal for that to happen. If we have a uniform distribution, my mean and my median will also be in the middle of that on top of each other. That's not what we're asking for here. It wants to know, it needs to have a mean that is smaller than the median. So that means we have to have something that drags my mean below. So that means if I stick on some extra things down here and I get some smaller values over here, that's going to force my mean to move that way. So we need to find something that is going to be skewed to the left. Okay, so we're looking for, we are looking for skewed left. Okay. So the salaries of the National Football League players, that should be roughly symmetric. Okay, yes, you're gonna have some really high, you're gonna have some low. Roughly symmetric. The scores of students out of on an easy essay exam in which most people get nearly perfect scores, but a few people do very poorly. That is going to be a skewed left distribution. We can go ahead and answer it. We'll talk about the other ones. Prices of homes in a large city, that's going to be skewed to the right. We're going to have just a few homes that are really, really, really expensive. Okay, the scores on a very difficult exam, that's also going to be skewed right because we're going to have a lot of low scores, and then we'll have a few people over here on the right hand side that did very well. And the amount awarded by civil court juries is probably roughly symmetric, would be my guess. So that's the one that hit home the best. Okay, 15 comes in at looks like 2341. The weights of male and female students in a class are summarized by the following box plots. So this is going to be another one where we interpret box plots. Which of the following is not correct? Okay, so we'll get on. This is easy on the not correct. About 50% of the male students have weights between 150 and 185. So 50%, remember, is going to be, that's going to be a box is the middle 50. Now, it could be 50% from your median above and below. So you have to pay attention to it. 150 and 185. 150 appears to be about quartile 1. 185 appears to be about quartile 3. So yes, A is good. That one checks. 25% of female students have weights more than 130 pounds. So 130 pounds checks in right here, and that's going to be my upper whisker. That is about 25%. So that one's going to check out. Okay. The median weight of male students is about 162 pounds. Median weight is going to be in the middle of the box, and I would say it's about 162 pounds. So that one checks out okay. The mean weight of female students is about 120 pounds because of symmetry. All right, now notice this one said median and this one says mean. So do notice that. Now because this is symmetric, that's going to be my mean and my median are going to be roughly the same. So therefore, yes, because of symmetry. And E, the male students have less variability, so obviously oh my God. Process of elimination gets us to this answer. Male students have less variability, so that means, but we see that's the wrong statement. We're spread out. My range is much larger, so that means it actually has more variability. Okay. All right, 16 is checking in at 2540. A company produces packets of soap powder labeled giant size 32 ounces. The actual weight of the soap powder in the box has a normal distribution with a mean of 33 and a standard deviation of 0.8. What proportion of packets are underweight, i.e. weigh less than? So again, this is going to be a normal calculation. Okay, didn't say it was normally distributed yet. We underlined it already. All right, so we're going to have a middle at 33, standard deviation of 0.8, less than 32. Again, this could be a case. This is typically a case where I'm going to go with a normal CDF. And within that normal CDF, my lower boundary is 1E99. We're going to top that out at 32. I'm expecting 33, and I have a standard deviation of 0.8. So again, this is going to be a free response question, even though I know this is multiple choice, but we need to practice getting your calculator speak in there. That's a mean mu, and a standard deviation. So we just needed to have that there. Anyway, we're going to run that in our calculator, and it's going to spit out something that's close to 0.106. Now this one I'm gonna walk through it old school, but let's go through and make sure we can understand how to do that otherwise. So we can actually do it with a z-score. That z-score is going to be the observed value, 32, minus the expected value, which is 33, and we're going to divide that by the standard deviation, which is a 0.8. So if I do that on my calculator, that gives me a negative 1.25. So just to practice this, we're going to pull in our z-table. Here is negative 1.2, and we're going to go over to 5, and there's the 1056, which round to 106. Okay, so again, that's how we got to it using the old, not old way, but by hand way. All right, so keeping it moving. Number 17, checking in at 2756. It's a density curve. So we have to remember that a density curve is going to have an area of 1. Okay, so this area has to be 1. And I know that since the area is 1, I know the bottom of the box is 2. So that means that this has to be 1/2. So when I take 1/2 times 2, I get an area of 1. Okay, now it wants to know for what percent of observations lie above 1.5. So there's 1.5, and I want to lie above 1.5. So I'm looking for the area of that box. Well, this box has a width of 0.5, and it has a height of 0.5. So we're going to take 0.5 times 0.5 and get 0.25, and that's answer B. What percent of the observations lie between 0.5 and 1.2? So again, same process. How wide is this? The bottom part from 0.5 to 1.2 is going to give me a 0.7. How tall is it? Well, it's the 0.5. So 0.7 times 0.5 is going to give me a 0.35 or 35%. So another B. All right. 29, 25. If the standard heights of 99.7% of Americans are between 5 and 7, what is your estimate of the standard deviation of the height of American male? So we didn't hit this earlier when we probably could have or should have, but let's review our empirical rule real fast. Okay, so there's my mean in the middle. or it could be 0 if it's standardized. So that means that if we go 1 standard deviation to the right and 1 standard deviation to the left, there's going to be a certain percentage that is that distance, and we know that 68% fall within 1 standard deviation. So we can bump it out further. We can move it out to 2 standard deviations, and we know that's to be 95%. Or in this particular problem, we can move it out to 3 standard deviations, and that's going to be 99.7. So I'm not going to try to squeeze it in there. I'll draw an arrow. That's 99.7. So we know that 99.7 is going to be plus or minus 3 standard deviations above or below my mean. Okay? Now, I know that, with the width of this is 6 standard deviations, I know it's going to go from, it looks like 5 on the left to 7 on the right. So it's a distance of 2 feet. What I have to notice is all that my measurements are in measurements of inches. So I know that 2 feet is going to be the same as 24 inches. And I'm going to divide that up into 6 different deviations. So 24 divided by 6 is going to be 4 inches. So C is going to and it's going to be where I end up on that problem. 19 checks in at 3107. Suppose the distribution of SAT math scores from your state this year is normally distributed with a mean of 480 and a standard deviation of 100 for males. And if someone scores a 780 or higher on the math ACT, can be considered a genius. What is the proportion of geniuses among male SAT takers? Okay, so here we go. There's my curve. We know that males are going to pop in the middle here at 480. They are a genius out here at 780. We're going to figure out what portion are geniuses. So again, I would truly roll this on a normal CDF on my calculator, just for speed. 780 is my left boundary. Infinity is my right boundary. It has a mean of 480 and a standard deviation of 100. Okay, again, lower boundary, upper boundary, mean, and standard deviation have to be all included. And if we do that, that's going to give me a 0.0013, which is going to give me a 0.13% roughly. And this is E is going to be my closest to that. Again, if we're doing this the other way, just to start us out, we could calculate a z-score. We observed someone at 780. We're expecting them to roll in at 480. And my standard deviation is 100, and that turns out to have a z-score of 4. So 4 standard deviations is way far to the right. So we know we should have a very, very small percent for that. Okay, 20 comes in at 3249. The average yearly snowfall in Chillyville is normally distributed with a mean of 55. If the snowfall in Chillyville exceeds 60 inches in 15% of the years, what is the standard deviation? Okay, so again, this is where it's going to involve an inverse norm because we have a percent that we have to get back to something. If it's an x value, we can use an inverse norm. Okay, but my problem is, I don't know what x value. I'm not shooting back for an x value. I know the x value, so we're going to have to use algebra for the win for sure on this one. Okay, so here we go. We're going to go with 55. We're talking about the top 15%. Okay, now I know that 1 standard deviation. Oops, let's go back and do that real fast up here because I forgot to do that. If I'm using up 68% in the middle, that means that 32 is left over, so a 1 standard deviation tail is 16%. Here I know this is 15%, which is going to be the same on the other side, so I know this is just going to be over 1 standard deviation. Okay, and the other one that we typically use, if it's 95%, I have burned up 95, that leaves 5 left over. So we're going to split that in half, and that's going to give me 2.5% for the other one. And then we can do the 99.7, but typically we don't see that, so I'm not going to go over it. But anyway, here we go. I need to have a z-score for this value right here. Okay, actually we know what it is. We know it's 60. But I need to know what that z-score is because remember we're going to go with z is equal to observed minus expected divided by my standard deviation. And in this particular problem, my unknown is going to be my standard deviation. Okay, so I need to know that z-score, so that's going to force me into an inverse norm. My area, now this is again going to be calculator dependent. Sorry, I didn't realize what the paper was. We could go with 15%. However, if you're going with your calculator doesn't have the left, right, center options, we have to know that we have 15% above is the same thing as 85% below. Okay, so we do have to know which way we're going to go with that. So we're going to have a 0, we're going to have a 1, and we're going to go to the right as far as if we're doing an inverse norm. So again, if we had distribution again, we're inverse norming. My area is going to be 15%. 0 is going to be my mean. 1 is going to be my standard deviation, and this is a right tail. Okay, to get that, and it turned out to be 1.04. And didn't we say earlier that we know this is going to be just above one standard deviation? Then that matched out what with what? Oh my God, with what we needed. So again, to finish this out, I observed 60. I expected 55. And now we have to have a standard deviation, and that is my unknown. So again, we have to have algebra for this one. Those two are going to switch places. So in reality, this is 5 divided by 1.04. And so that's going to give me some value, 4.83. Okay. 21 is checking in at, what is that? I think that's a 36. 36.26. If a median of a set of data is equal to the mean, okay, we talked about this earlier, okay? It could be if it is symmetric, it could be if it's normal, okay? But remember, that's not necessary because it could be symmetric, okay? And my mean and my median will match up on that too. So therefore, my best answer is down here. It is symmetric. It's not going to be skewed. Approximately distributed means nothing. And we can't say anything about the shape with any certainty. Well, my mean and my median, you're going to know that it has symmetry. Okay, so we're done with 21, and we're done with the free response, the multiple choice questions. All right, gonna move into free response real fast. So here we go. We have school A and school B. What do we know about them? A teaching year is recorded as an integer. Oops, what are we? Sorry about jumped the gun. 3730. All right, we know that we have 200 teachers over here in school A. I jumped the gun. I suppose I should read. Teacher year is recorded as an integer, with first year teachers recorded as 1, second year teachers recorded as 2, and so on. Both sets of data have a mean teaching year of 8.2, with data recorded from 200 teachers at high school A, which we already recorded, and 221 teachers at high school B. On the histograms, each interval represents the possible integer values from the left endpoint up to, but not including the right endpoint. So, for example, in this one, this is in first year teachers, second year teachers, and third year teachers are included. That one, fourth year teachers are going to go up into the second bar. Okay. All right. So identify the teaching year for, the median teaching year for one high school is 6. The median teaching year for the other high school is 7. Identify which high school has each median and justify your answer. Okay. So we have to remember a median. Your median is the middle number. It has a formula. Technically, it's n plus 1 divided by 2. There's other ways to get there, but this is going to be for high school A, we're going to take 201 divided by 2, which is going to give me 100.5. So I know this is going to be the 100th student, 100th teacher. Good gravy. All right, so I know I have 46 in this one. I know I have 47 in that one. So if we add those together, that gives me 92. Well, I have to get to the 100th student, so that means that the 100th student has to fall in that bin 7 to 100. Okay, so 7 to 10. My God. Anyway, so that means that high school A has a median of 7 since its 100th teacher lies in the 7th, 8th, or ninth years of teaching interval. So if we go over to this was for the median for A, so the median for B, this is going to be 222 divided by 2, which is going to be 111. So there's going to be my median for school B. So again, if we do the same exact thing here, I kind of covered it up. Sorry, I didn't mean to do that. Guess I should look at my screen. Anyway, I'm going to roll with there's 79 teachers there, and there's 34 teachers here. So that means if we have 79 and we add that to 34, that's going to give me to 113. We're after 111, so that means 113 has to fall there. So that means that, and that verified what we knew, high school B has a median of 6 since its 111th teacher lies in the 4, 5, or 6th year interval of teaching. Okay. An additional 18 teachers were not included in the data recorded from the 200 teachers at high school A. The mean teaching year for those 18 teachers is 2.5. What is the mean teaching year for all 218 teachers? So we have to remember the mean. The mean is going to be the sum of all years divided by the number of teachers. That will give us my average. Now the sum of all years is what we're going to have trouble with here because I have two groups of teachers. I have the 200 teachers that have taught for, where's that up here? Each one had a mean of 8.2. So I have 200 teachers that have taught at a mean of 8.2. So if I multiply those two numbers, that will give me the total years taught by all those teachers. But I also have a group of another 18 teachers here, and I have to figure out how many years they have taught. Well, we're going to take that 18 times 2.5, and that will get them covered, and we're going to add those together, and we're going to divide that by the 218 teachers that there are. So if we do that, we come out with 7.73 years. Okay, so again, that's where we're going to roll on that one. So remember, we always want to show work when we show work as much as we can, because that's what a lot of times we'll get graded on. All right, our last question before I go horse. The standard deviation of the teaching years for the 221 teachers at high school B is 7.2. If one teacher is selected at random from high school B, what is the probability that the teaching year for the selected teacher will be within one standard deviation of the mean of 8.2? Justify your answer. All right, so again, we'll go back to a probability. A probability is found by taking the favorable outcomes and dividing that by the total outcome. Well, the total outcomes is easy. That's going to be 221. But we have to figure out what is my favorable outcome. My favorable outcomes is if I am within one standard deviation of 8.2. So what is one standard deviation of 8.2? Well, that'd be 8.2 plus or minus my standard deviation, which is 7.2. So when we take 8.2 minus 7.2, we're going to have a left boundary of 1. If we add those together, we're going to get a right-hand boundary of 15.4. And again, because this is fairly irrelevant as far as 15.4, we don't have decimals there, so that gets truncated off to 15. Okay, so we're talking about 1 to 15. So we're gonna have to come back up here, and we're gonna have to estimate that there are 28 in 7 to 10. There are 29 in 10 to 13, And then there are 19 in 13 to 16, because then 15, excuse me, 13, 14, and 15, because 16 moves on up. So here we go. Excuse me. Okay, so we're gonna skip over this. I don't know what that step was. We're gonna come back up here so you can actually see what I'm writing. And we're gonna go with, we got 79 plus 34 plus 28 plus 29 plus 19. And again, we're gonna divide that by 221. So that turns out to be there's an 85.5% chance that they will fall within one standard deviation of the mean. Okay. Hopefully that helped, embellished a little bit where we could. And again, it's just a good all-around review of things about descriptive statistics. So thanks for listening. Have a great night or day or whenever you're listening to this.